Okay, so we start the sixth module, which is forms of learning. So there's two kinds of learning. One is with a teacher that's supervised, one's without a teacher. That's two types again. That's either reinforcement learning or it's unsupervised learning. There's a diagram on the right. So if you zoom in, you'll see environment. This is reaction. This is learning. This is a summation of that leads to an error signal. It's a minus here for the learning and a plus for the reaction. There's a vector that you feed into the reaction. So in supervised learning, you have a teacher that gives you knowledge. Therefore, you know what an optimum response is. You have a training vector and you have an error signal. And this error signal is the difference between the desired response and the actual response. The second is reinforcement learning, where you learn through continued interaction. This is based on feedback from critics, and you want to maximize utility at the end of the day. The third is unsupervised. You have no external teacher, you are independent, and theory, you probably get differences here, right? So supervised learning, unsupervised learning is predictive, descriptive, classification, regression are examples, clustering, k-means are examples. Naive Bayes is an example of supervised learning. Here there's input-output mapping. Here's this no such thing. And here you have a labeled data set, and here you have hidden learning patterns instead of a labeled data set. So most of your questions from this module will come from dimensionality reduction, and there are a few ways to do that. The first is principal component analysis, arguably the longest of them all. So you will be given two sets of values, and there'll be about so we'll just learn this through an example, right? So let's say there are four samples and x1 and x2. So first thing you want to do is find the mean of both x1 and x2. Here we found 0.5 and 1.5, fairly simple. Um, the second is you find the covariance matrix. So this is the formula for a covariance matrix, right? 1 by n minus 1, the summation of I 1 to n, x of ik minus xi mean minus x of times x of jk minus xj of mean. Here n is the number of samples, which is 4. And well, so the way this is expanded is, let's say this is a matrix, right? So this would be S12, x1, x13, x14, x21, x22, x23, x24. So this is x11, sorry. Yeah. So this is your matrix. So let's say that we are trying to calculate the covariance of the first element, which is S11. So your I would be 1, your J would be 1. You substitute all of that in, you see that the form is expanded here for the first element. You get 1.667. Usually, you should end up getting the same value for these two because mathematically they're the same formula if this dimension is the same. So eventually, applying this formula, we get these values: covariance matrix 1.667, 2.667, 2.667, 4.333. The second step is to find eigenvalues. The formula for this is you have to equate the determinant of S minus lambda I to 0. So S is the covariance matrix, lambda is just lambda, the eigenvalue, and I is the identity matrix. So when you do this, you get um minus lambda 0 minus lambda 0 0 minus lambda as this matrix. So when you um subtract that, you have 1.667 minus lambda, and here since it's 0, so it's 2.667 here, and then you have again 4.33 minus lambda. It becomes a quadratic equation. You solve for it, you get lambda 5.98, lambda 0.02. You want to prioritize the larger lambda, so we take lambda is equal to 5.98. The next step is then to find the eigenvector for this. So the eigenvector is defined as u1 u2 as a column vector. So the equation here is 0 0, or just 0 is equal to S minus lambda I times the eigenvector, or this is your equation. So for this, we get the value of u1 as 1 and 1.62. Now, since these are the values, we have to normalize them. And the way we do this is we divide each of these elements by the magnitude of the vector. So magnitude of the vector is given by root of 1 square plus 1.62 square, which is 1.9. So we divided both of those. We got these values 0.526 and 0.852. Similarly, we want to repeat this for lambda is equal to 0.02, not really necessary, but the final projection that you're going to get is y, and y is equal to xv, where here x is not the same matrix that we had, but x is actually xi minus x bar. So minus 1.5 is essentially minus 1 minus the mean that we had here, which was 0.5. So -1 minus 0.5 is -1.5. Then you take this row and you do the same thing for 1.5 being the mean, and then uh, well, 0.5 being the mean, and then you take 1.5 for the second row, and you convert that into the second column here. So this is one column, this is two columns. Then you take the unit eigenvector and you multiply this and you get the value of y projections for lambda is 5.98. Usually you don't need to find the value for the other lambda. So this should be enough, but otherwise it's just a repetition process. As for regression, so this is just a y equals a plus bx thing. There's a formula for this summation of x minus x bar into y minus y bar. Blah blah blah. A is equal to summation of y minus b of summation of x by n. N is the number of samples here. So again, best looked at through an example. You have these values for midterm x and final y. So this is x column, this is y column. You have to find what the final score is. Suppose that midterm score is 86. So y is equal to a plus bx. Obviously, you have to find b first because b is in the formula of a. So the easiest way to remember this is to draw four columns next to this table always, x minus x bar, y minus y bar, and then the product of these two, and then the x minus x bar, the whole squared, and you sum all of these. Now you plug in, again, you sum all of them, you find b, and then you find a. It's fairly simple. You sum y, it's just all the values of the column y, sum x, all the values of column x, b times summation of x divided by n, and then you find a and b, and then you plug it in to this equation, y is equal to a plus bx, where x is equal to 86, b is equal to the value you get, a is equal to the value you get y value. So here we have the values, a is equal to 32.02, b is equal to 0.5816. The next method is k-means clustering. This is unsupervised, it's centroid based. So initially you're given k, a number of clusters, you're given a set number of points. So you have to tabularize these or tabulate these. Euclidean distance, the formula is fairly simple. So usually they give you the centroids that you need to take, but here we can just assume initial centroids to be A1, B1, and C1. So here we've organized the data into two columns, and then we've put the three centroids in separate columns here. And these entries are the distance between that point and this. So for example, 2, 10, 2, 10, the distance is obviously 0. The way it's calculated is 2 minus 2 the whole square plus 10 minus 10 the whole square. Similarly, if it were 5, 8, and 2, 10, then you would be doing 5 minus 2 and 10 minus 8, the whole square, and then sum that, and then you'd get the distance. So you'd fill in all these values. It's an excruciating process, but once you get to the end of it, your job is to find which distance or which centroid each point is closest to. So for example, 2, 10, the A1 point is obviously closest to the centroid A1, which we took. But B2, 7, 5 is closest to 5, 8 because its distance is least here, which is 3.61. Therefore, since this is a second centroid, we're assigning this to the second centroid. And this column is all you need to focus on for now. So we have our initial list of clusters here. So we have one element in the first cluster, two in the third cluster, and the rest of the five are in the second cluster. So from this cluster, we want to calculate the new centroids. And the way we do this is we take each cluster. So the first cluster, there's only A1. So the new centroid is again A1. For the second cluster, there are 5 points. So we take we divide that by 5 and we sum that. So we get 6, 6. So basically take the mean of these 5 points. Again, for the third cluster, since there are 3 points, okay, there are 2 points, but the summation is 1.7, 1.5, 3.5. And you repeat this process and you get a new cluster, which is C of n. So basically this column is added after you do the whole distance thing. And again, so you make a new table, you evaluate the distance between the new centroids and these points, and then you get a new set of clusters. So you repeat this process until each cluster is the same in both of these rows. Here we have a mismatch. It's a 2-1 mismatch here. So we repeat this until C is equal to CN. Then it is truly over. Next is k nearest neighbors. So again, we've gotten two columns and we have a class division. Now, this is again distance formula based. We're given a height of 170, a weight of 57 kgs. We're asked to predict what class they are in. So under is U, normal is N. So it's the same formula that we use the distance. We want to minimize distance and we want to sort this by least to highest distance. And let's say we have been given, let's say these three are actually the least, are the ones with the least distance to our predicted required to predict point. So assuming that these three are the top of the table, even after we assign them in an ascending order, then for k equals 3, we would take the first three values. And here, normal occurs two times and underweight occurs once. So because k is equal to 3, we consider the first three values after we rank it in an ascending order. And in that, the majority is normal. Therefore, our prediction is normal. If our top three values were the bottom three, which were actually sent to the top in an ascending order, then for k equals 3, our prediction would be normal because n is equal to 3 out of 3. It's always normal. That is k nearest neighbors. Z-score normalization, we've already looked at the previous module, but again, an example to illustrate that point is the same formula, z equals x minus nu by sigma. Here, this is the mean of each variable. So for AIML, your mean would be the summation of AIML column divided by 5 because there are 5 observations. You get 82. This sigma, you would get the summation of xi minus x bar, the whole square, but divided by n. So this is basically you take each term, you subtract the mean from it, you square that value, and then you add all of that for the whole column, and then you divide by 5, which you get 5.9. So for the first entity here, 75, your Z normalized score will be 75 minus 82 because the mean is 82 and divided by 5.9, that's minus 1.19. And then you do that for every single element in that column to get the AIML Z score normalized values. So decision trees. Decision trees are a bit annoying, but yeah, this is okay. Information gain is where it starts to get useful. Entropy is the degree of randomness of data. So this is a basic formula of entropy. Um, Negative of summation of probability of I times log 2 of probability of I. Um, so this is just an annoying formula to look at. So just don't. Information gain is the entropy minus the entropy of a subset weighted value. So again, you can ignore the formula for now. It's better understood via an example. So here, the global entropy for this table is going to be the summation of the probability times the log 2 of that probability of each class. So the probability of a mammal is 1, 2, 3 out of 7. So 3 by 7 log 2 of 3 by 7 plus bird, which is 4 by 7. So 4 by 7 log 2 of 4 by 7. Then you take the negative of that because that's there in the formula. You get 0.985. And then to get the information gain, we split. So we split, let's say we split based on color. And we have two colors. So in brown, we have two birds, one mammal. Your E of entropy of brown comes to 0.918. You have to calculate the entropy of this separately. So it would be 1 by 3 log 2 of 1 by 3 plus uh, 2 by 3 log 2 of 2 by 3. And then you negate the whole thing and you get 0.918. And then here, since you have two birds and two mammals, your entropy of white is 1. So because these are subsets, you also have to weigh them. The quantity of the subset is 3. So 3 by 7, which is the whole data, 3 by 7 times 0.918 plus 4 by 7 times zero point 0.1 is 0.965. And this is the entropy of the split. The gain is given by the total entropy minus the entropy of the split, which is 0.985 minus 0.965, which is 0.02. You can ignore this for now. Gini impurity is an alternative to entropy. It's practically a similar formula, 1 minus summation of pi square. The only difference is a faster computation process. There's a 2% disagreement rate. Doesn't really matter. Nobody cares. Pruning, we reduce the size of a decision tree by removing unimportant branches. Regularization reduces complexity and overfitting. Yeah, that's all. So next thing is handling numerical attributes. Um, honestly, this, okay, cool. Let's consider this table. Here we have two columns. So let's ignore this for now. So let's look at the humidity column alone. First thing we want to do is sort this in an ascending order, which we've done here. The second thing we want to do is calculate the gain of that column. The way we do that is by subtracting the split entropy from the global entropy. We know how to calculate global entropy already, which is 9 by 14 log 2 of 9 by 14 because, well, the probability of yes is a 9 by 14, probability of no is a 5 by 14. So 5 by 14 log 2 5 by 14 is 0.94. And the first split, which is a less than or equal to t. So here t is going to be the midpoint. So you can ignore this column actually. I've never really figured out why we're supposed to calculate means and everything. Um, so you're actually supposed to find the highest gain among all of this for each row, but that's too long. It's honestly very annoying. But x of a lesser than t divided by x is the weight. Entropy of that specific part, which is this column, including 80, is minus 7 by 14 because, well, that is the weight. So it contains 7 of the 14 values of the table times. There are 6 yeses here. So 6 by 7 log 2, 6 by 7 plus 1 by 7 log 2 of 1 by 7 is probability of no. It comes to this. Similarly, the bottom half of the table, your weight is again 7 by 14 and your entropy comes to 0.98. And you multiply this, your overall gain comes to be 0.52. So you repeat all of this and it's shown that the gain is highest for this row. That is how to calculate the gain and entropy for a column. How to apply this in a question we'll look at later. So bunch of theory before that. Handling missing values, there are a few ways. You set to most common value, you set to a most probable value, you add a new instance, or you discard it. C4.5 algorithm handles all of the above and it does post pruning. So decision trees introduce nonlinear boundaries. So random forest and other theory thingy. You build many slightly different decision trees, combine multiple learning algorithms like bagging, random subspace boosting. You have bias, which is assumptions of a model to make learning easy. You have variance, which is delta of error over multiple instances. So how much does your error differ over multiple iterations? So in complex models with low bias and high variance, you're overfitting. You have overfitting, and when you have high bias and low variance, then you have underfitting. Underfitting happens in simple um, systems, while overfitting happens in complex systems. So when you have a lot of data points, then the model takes into account too many values and it overfits. So ideally, you would want a low bias and a low variance. So to reduce this, you want to simplify, you want to remove features, you want to regularize, and you want to put an early stop. So this is to reduce overfitting. To reduce underfitting, you want to add more data, you want to decrease the regularization, and you want to train for a longer time. So naive Bayes classifier. Probabilistic classifier based on a bunch of things, theory, classifier model, theory. So you've given this, and you're given that the question is, well, if confidence is yes, sick is equal to no, will you fail or pass? First thing you do is find the prior probability, which is probability of R equals P, probability of R equals F, which is probability of passing and probability of failing. And then you find the likelihood probability, which is probability of C is equal to yes, which is confidence equal to yes if you are passing, probability of confidence equals yes if you are failing. So we get as 2 by 3 and 1 by 2. And probability of S is equal to no, R is equal to P, 1 by 3, 1 by 2 again, which is basically deriving from these tables, right? So FP is here, YN is here. Then you find the posterior probabilities. So probability of X given R is a pass, is the probability of C equals yes, given that R equals pass, probability of S equals no, given R equals pass, which is 2 by 3 times 1 by 3, which is 2 by 9. Probability of X given R equals F is 1.1 by 4. And then you have the final expression, which is just multiplying the two. Is probability of X given you pass, and then probability of passing, you multiply the two, 0.133. Probability of X given that you're failing, and then probability of actually failing, which is zero point 0.1. Therefore, the probability of passing is greater than the probability of failing. So you are going to pass. That is the prediction. So that's it for module 6. We'll do questions relating to module 6 in the next video as well.